Good morning, class, and welcome to this lesson on Fluid 7, Equation of Continuity. Today we will be able to define ideal fluids, mass flow rate, and volume flow rate, and give conceptual examples of each. So, first off, let's start off with an ideal fluid. An ideal fluid. So an ideal fluid is a fluid that is incompressible, non-viscous, and it experiences no turbulence. No turbulence. Or we also call that steady flow. Steady flow. So just like in kinematics, where we say that there's no air resistance, we say we have ideal fluids, because when we have ideal fluids, that makes our math a little bit easier. So incompressible. Let's say I have a piston here, and this whole thing is full of water, H2O. Incompressible means that if I push down on this piston, it will not compress any further. It will the max that this piston can go down is right here, and if I cannot push it down any further. If I push down any further, the container will rupture. As opposed to like air, you know that if you have like a syringe or a piston full of air and you push down, the air molecules would end up compressing down into a smaller area. Okay? So we're going to assume all fluids are incompressible. They cannot be squished, so to speak. Viscous, viscosity. Viscosity is also kind of known as thickness or stickiness. Viscosity is the resistance to flow. So for example, honey is much more viscous than water. Water flows very easily, and honey flows less easily. It's thicker than water, so it's said to have more viscosity. So we are going to assume that fluids are non-viscous, because viscous resistance to flow is kind of like friction. And like before, if we get rid of friction, it makes our math a little bit easier at first. So because this is AP Physics B, we're going to stick with incompressible fluids that are non-viscous. And turbulence means steady flow, meaning if it was flowing, think of like whitewater rapids. You have water that is crashing down and frothing back up, and then crashing down again and frothing back up. It's very, very turbulent. It has very, very sharp turns in its flow because there's rocks and stuff underneath the water. Well, steady flow means it's going to be exactly what it sounds like. It's going to be steady. There's no sharp turns. There's nothing like that, because those sharp turns and that turbulence will affect our math. So we're going to assume it's steady flow. So these are ideal fluids. We're going to assume all of our fluids are ideal fluids in AP Physics B. So what does that mean? What are we talking about here? So we have ideal fluids. Well, really we're trying to figure out, what is this mass flow rate? Before, we were talking about fluids that were steady state, so fluids that were just kind of sitting there. So we looked at, what would be the pressure down here on a fluid, and so we found a pressure to be the atmospheric pressure plus rho GH. But now we're going to be looking at fluids that are going through some sort of channel or canal or pipe or something, and now they're moving. So because they're moving now, we're not going to have the same sort of equations. So mass flow rate really is mass flow rate is exactly what it sounds like. How much mass of fluid, is flowing per given time period. So we have a mass of fluid flowing, and how fast is it flowing? So it's kind of like velocity. But once again, we have trouble. With this value here with mass. It's very hard to measure the mass of a liquid. So what do we do with the mass of a liquid? We know that density is mass over volume. So mass equals density times volume. So mass flow rate is going to really be the density times the volume over time. Now, to further manipulate this equation, volume is the same thing as area times a distance, over time. And if we look at this right here, distance over time, we get density times area times velocity. Density times area times velocity. And mass flow rate, I guess we can say, is conserved, so to speak. And so the density times the initial area times the initial velocity is going to equal the density times the secondary area times the secondary velocity. And because our fluids are incompressible, this density is going to be the same density on both of them, so we can cross that out. So our mass flow rate equation is going to be area times velocity equals area times velocity. Now, all right, so we have this equation here, but what does that really mean? Let's go look at a very, very common situation. You have a water hose. And water is flowing out. Water is flowing out of the water hose, okay? But you're watering the lawn and you want to increase the range of the water hose. So what do? You take your thumb and you put it over the end of the hose. So your thumb is right here now. And you get a spray of water that's coming out much further than it was before. Well, why does that happen that way? Did you magically somehow make the water go faster? What really was happening? Well, this water hose has a certain area, and the water coming out has a certain velocity. Well, here, what did we do? We decreased the area. And because we decreased the area, we increased the velocity. So A1 V1 equals A2 V2. So let's just say the area of this is 3 centimeters, and then when you put your thumb over, it's 1 centimeter. So 3 centimeters squared times, and we'll say it's going 1 meter a second, times 1 meter a second equals 1 centimeter squared times V2. How fast is water flowing out? Well, we divide by 1 centimeter a second squared, and the centimeters cancel out out to 3, and so we get 3 meters per second. Because we decrease the area, we increase the velocity. Because we decrease the area, we increase the velocity. So if we ever have fluids flowing through tubes, kind of like this, because some tubes get reduced down, conceptually, we can assume that because this has a smaller area, the fluids moving here are going to be moving faster. This is greater than. The fluids over here are going to be moving faster than the fluids over here. So this is mass flow rate. Okay? Now, let's look at a very, very related term, volume flow rate. Volume flow rate. And volume flow rate is exactly equal to mass flow rate. We just manipulate the equation around a little bit. So let's look at our equation here. A1 V1 equals A2 V2. Well, if we manipulate this side right here, velocity is the same thing as distance over time, A2 V2, and area times distance or area times height is equal to volume. So volume over time equals A2 V2. This is the exact same thing as as mass flow rate, but let's say the question's saying how long does it take? Well, we have delta T right here, and so we can manipulate this equation right here to solve for delta T. Or what volume of water flows out of the system? Well, we have the volume right here. So I'm just showing you another way to solve for problems depending on what they're asking for. Maybe they're not giving you area and velocity. Maybe they're giving you area, velocity, and time. You have to solve for volume. So volume flow rate and mass flow rate are the same thing. How fast does a volume or a mass travel through a certain area? So we've defined mass flow rate, volume flow rate, ideal fluids. I'm now going to show you a common thing that happens in most questions, so that way you can look out for it. Most of the time, water or fluid flows through a circular pipe. Okay, it flows through a circular pipe, and we'll say it's going from a smaller pipe to a larger pipe like this. And most of the time, the question is not going to give you the area. The question is either going to give you the diameter of this, or it's going to give you the radius of this. Okay, so it's either going to give you the diameter, capital D, or the radius. And because you are given the diameter or the radius, you have to solve for area. And so the area of this section right here is pi r squared. So A1 V1 equals A2 V2. This is the same thing as pi r1 squared V1 equals pi r2 squared V2. Now let's say this radius right here is 1 centimeter, and this is 4 centimeters. So my radius here is 1 centimeter squared V1, and this is 4 centimeters squared V2. You might notice already that the pi's cancel out, so that's kind of nice. Now, because this is 4 times as large, I know in my head that the velocity is going to be 16 times less. Why is that? Because these values are squared. Because if I solve for this, this is going to be 16, so I divide both sides by 16. So V2 is going to equal 1/16 of V1. And so what I'm trying to show you here is that the radius is equal to each other by a squared value. So if this was double the size, velocity here would be 4 times less. If this was 3 times the size, the velocity here would be 9 times less. And vice versa, if we were going the other way, if the flow is happening that way, because this is 4 times smaller, the velocity is going to be 16 times greater. So I'm just trying to give you a quick conceptual understanding of how this equation works, because you can do some very quick math in your head if you understand how these two are related, okay? So area and velocity are inversely related. When area goes up, velocity goes down. When area goes down, velocity goes up, and they are inversely squared related. So when area goes up by 2, velocity goes down by 4. So these are an inverse square relation.